When it comes to Rheoelastomers, the RPA can be a powerful tool for analyzing material stability and identifying potential mixing or processability issues. It provides viscosity data, helps us detect long chain branching, and gives insight into thermal properties. We can also use it to correlate with Mooney viscosity, and once that correlation is established, you may not need a separate Mooney Viscometer for routine testing. The RPA can even help evaluate molecular weight and molecular weight distribution variations across different batches. Beyond that, it allows us to determine the linear viscoelastic region, run stress relaxation tests, and detect the presence of gels. With the time temperature superposition, which is TTS, we can broaden the shear rate range significantly, making it possible to simulate high shear processes like extrusion and injection molding. And of course, the RPA is fully capable of performing standard tests according to ASTM, DIN, and ISO protocols. All right, so when it comes to mixed compounds, the RPA can be used to evaluate filler dispersion and determine the degree of silicization. You can run MDR-like isothermal cure tests, as well as non-isothermal tests to simulate real-world temperature profiles and observe how the material responds. It can also be used to perform cure kinetics analysis, monitor blowing or foaming reactions, and check if the material tends to swell during extrusion. Stress relaxation testing is possible as well, along with after-cure property evaluation. And of course, the RPA, again, can be used to perform all the standard tests defined by ASTM, DIN, and ISO. Let's begin with the instrumentation. So on the left-hand side, you'll see an actual image of the RPA testing chamber. On the right, there is a schematic drawing showing the key components inside the chamber, including the torque transducer, temperature sensors, heaters, seals, upper and lower dies, and the direct drive motor. Now, let's take a closer look at each of these components separately. So we'll start with the torque transducer. This component measures the torque generated by the sample as the lower die oscillates. The upper die is stationary and directly connected to the transducer, and the torque values range from 0.02 dNm to 240 dNm, which is why the RPA is considered a high torque rheometer necessary for testing Rheoelastomers and mixed compounds. Optionally, the RPA can also be equipped with a pressure transducer, which measures the normal force or cavity pressure. This is especially useful for tracking blowing or foaming reactions. With this setup, you can adjust the cylinder pressures up to 90 psi to minimize the slippage and monitor cavity pressures up to 5,000 psi. Next, we have the direct drive motor, which controls the strain amplitudes. The motor covers a wide strain range from plus or minus 0.07% up to plus or minus 1255%, which translates to roughly 0.005 degree to 9 degree. And then the frequency range goes from 0.0016 Hertz up to 50 Hertz, giving you fine control over test conditions. Then there are highly sensitive temperature sensors and heaters. On top of that, the standard RPA system can operate from ambient temperature up to 230 degrees C. For more demanding applications, there is high temperature option that extends the upper range up to 350 degrees C. We also offer a sub-zero cooling option, which allows testing from minus 25 degrees C to 230 degrees C without using liquid nitrogen. Here we have the dies. The upper die is a stationary plate connected directly to the torque transducer, while the lower die is the moving plate driven by the direct drive motor. These dies are designed with a unique geometry, a biconical or cone and cone shape, which ensures a uniform strain field during testing. And one of the key advantages of the RPA is its closed cavity design. Unlike open cavity rheometers, which can suffer from edge fracture or slippage at high frequencies, the closed cavity helps eliminate those issues and ensures more reliable and reproducible data. There is also an overflow channel which captures any excess sample to ensure proper sample flash. That flash actually acts as an additional layer of encapsulation, helping maintain the test consistency. Finally, we have seals, which prevent the material from leaking into the hardware components and help reduce friction between the dies and the seal plates. Okay, so let's talk about the operation principle. One of the great things about the RPA is how operator-friendly it is. All you need to do is load the test method into the software, place the bottom film, add your sample, cover it with the top film, and hit start. That's it. The Rheometer takes care of the rest automatically. Pretty simple, right? After the platens close, the test begins by applying a sinusoidal deformation, which we call this as a strain. You can think of it like gently pushing and pulling a spring back and forth. In response, the material resists this motion, generating a measurable reaction called torque, similar to the spring pushing back against you. On the right-hand side, you can see something called a phase shift, labeled as delta, between the applied strain and the resulting torque. This is kind of like the lag you feel when you push something really heavy. It doesn't move exactly in sync with your effort. When we take the tangent of this phase angle, we get tangent delta, a key parameter related to processability. Now, it is important to note that the only quantity the RPA directly measures is torque, represented here as S star. This isn't a unique property to the RPA. It is true for all strain-controlled rheometers. Torque is always the primary measured variable. This torque value captures both the influence of the instrument's geometry and the material's response under deformation. From that single torque measurement, we calculate other important parameters, including G star, which is complex modulus, G prime, storage modulus, and G double prime, loss modulus. And these values then allow us to determine tangent delta and eta star, which is the complex viscosity. Let's take a brief look at the viscoelastic data here. So first up is S star complex torque, or G star complex modulus. This represents the total resistance to deformation, a combination of the material's solid-like and liquid-like behavior. You can think of it as how much the material resists being shaped overall. Next, we have S prime, elastic torque, or G prime, storage modulus, which reflects the elastic or solid-like response. It is similar to a spring or a rock. It stores energy and tries to return to its original shape after being deformed. Then there is S double prime, viscous torque, or G double prime, loss modulus, which represent the viscous or liquid-like behavior. Moving on to the eta star, which is complex viscosity, this tells us the total resistance to flow. It gives us a sense of the material's thickness or stickiness under an applied force. And finally, tangent delta, the dampening factor, is the ratio of G double prime to G prime or S double prime to S prime. This is the phase angle, and then the phase lag. It shows the balance between the material's liquid-like and solid-like behavior. A higher tangent delta means the material flows more, while a lower value indicates more elastic and solid-like behavior. Again, it is important to remember that in the RPA, we set the inputs like frequency, strain, temperature, or time, but the only variable directly measured is S star, which is the torque. All the other values, S prime, S double prime, G double prime, G star, eta star, and tangent delta are calculated from that single measurement. Together, these parameters gives us a detailed view of the material's viscoelastic behavior.